Yeah, today I'm going to give a talk about some content that I think everyone here is quite familiar with. So, singular learning theory and its applications to safety. So, a lot of the pieces of this talk I've given in other talks at other various points in time, but I've tried to pull it all together to tell the coherent story of how we see SLT fitting into the broader AI safety picture, its applications for interpretability, alignment, and more broadly. And so that's what we're going to tackle today. So I think the starting point is the recognition that AI is progressing very quickly, right? And right now we're operating out of an assumption, or at least I am, that AGI is something that's on par with humans will be here in the next 2 decades, give or take. So soon. And in particular, I think there are two trends that are surprising and a cause for concern. So on the one hand, the scaling laws tell us that you can convert data and model size into better performance. So consistently, just by throwing in more of these macroscopic variables, you have this currently empirical guarantee that the model is going to get better at the other end. On the other hand, predicting performance on any specific downstream tasks is very difficult. So there are these emergent capabilities where if you look at a specific task like mathematical reasoning ability, progress is often much more jumpy and not as smooth as predicted by the scaling curves. So it's this tension between the the certainty, the near certainty that performance is going to continue improving, combined with the fact that where that performance improvement is going to come from, we don't know. That I think is a source of uncertainty and tail risk worth taking seriously. Okay, so we're in a bit of predicament where we may soon find ourselves with a competitor species, or at least a species that is as intelligent and capable as we are. And often when you find yourself in a predicament, I think it's useful to ask yourself, well, how did we get here? And it started right around here, right, with the start of the deep learning revolution at the start of the 2010s. Deep learning started working in practice. And this is despite what the classical theory of learning predicted, right? Classical learning theory predicted that making models bigger, making them over-parameterized, making them as large as we started making them for computer vision tasks and then natural language tasks would make them overfit. That wasn't the case. Larger is consistently better. Okay, so we start with a scientific mystery, really, that is the start of the recent empirical boom in the success of deep learning. When you find yourself in this situation like this, maybe it's helpful to dig a little deeper and go towards the root cause of this whole predicament. So what is it, if deep learning is the cause of this current situation, what is it that makes deep learning so special? What makes it work? I think the answer is that deep learning systems, deep neural networks, are able to learn algorithms. I think this recent work from Anthropic, studying a range of algorithmic structures inside of models, really just clenches the case. Neural networks learn these rich these rich internal representations that they compute on in a sequential hierarchical way to compute outputs and make predictions of the world. This isn't just shallow lookup tables. There's something deep and structured going on here. Okay, that makes neural networks quite unlike previous statistical learning machines. Approaches like regression, Gaussian processes, or clustering, right? None of these classical techniques is ever going to learn how to, for example, sort a list. So there's something special about deep learning systems that makes them able to flexibly learn different kinds of algorithms, to learn the right algorithm for the task at hand. So what is it about deep learning systems that lets them do this, that lets them learn algorithms? Well, the idea, or one idea that we'll be exploring today is that maybe it's the same reason that the classical learning theory breaks down, that this prediction that neural networks should overfit, that's the wrong prediction. Maybe that's also the explanation for the fact that neural networks are able to learn algorithms at all. In particular, what SLT says is that you look at the loss landscape associated with these neural networks, it's incredibly degenerate. So different regions of parameter space have different qualitative shapes associated to them. And this is associated with the fact that different regions of parameter space encode different kinds of algorithms. Different algorithms, different local geometries. And this breaks classical learning theory. So yeah, the key idea here, there's one idea to take away from this talk, is that SLT suggests the geometry of the loss landscape is key. It's key to understanding what's going on inside of neural networks. This is applications for interpretability, and it might be key to steering models more reliably. So that is alignment. So we're going to talk first about AI safety and flesh out the consequences of these ideas a little bit more for a safety perspective. Then we'll talk about SLT. I'll go back to the basics and introduce some of the fundamentals of SLT. We'll look at the problem of generalization. So why do neural networks work as well as they do? Finally, we'll look at the learning process and where these learned algorithms come from. So starting with safety, I'd like to come back to the observation that many of the practical problems we have in safety, where we don't necessarily know what we're going to get out the other end when we define a deep neural network learning process, are really scientific in nature. So we don't have the scientific understanding needed to safely engineer in practice powerful AI systems. For example, right, the question of how data gives rise to internal structure models, what algorithms are learned, the problem of learning, is related to the question of how do you choose the right data to shape this learning process to give you the algorithms you want. Typically, learning is underspecified. How do you specify this more completely? How do you align models? Similarly, on the other end, the question of how the algorithms that neural networks learn enable them to generalize so well, the link between internal structure and generalization is closely related to the question of interpretability. What parts of these algorithms are responsible for a given set of behaviors that you observe? So can you attribute behaviors that the model is exhibiting or changes in generalization behavior to parts of the model? And then again, link them back to the data that the model is trained on. So maybe we need to develop this scientific understanding further. Consider the fact that currently, the way we actually align models, the way we actually steer them and try to program these models very much resembles alchemy, right? So we've got these three basic ingredients. We've got the cauldron, that's the architecture. We've got some reagents that we're mixing together in the cauldron, it's the data. And then we have the optimizer. So it's the flame that causes these reagents to combine and undergo chemical transformation. What we get out the other end are algorithms, right? New compounds, new chemical compounds. Now, the question I'd like to ask is where do algorithms come from? So which of these three inputs, if any, is most responsible for the algorithms that the model comes up with? Now, I'd argue that it's not the architecture, right? Whether you use a cauldron made of wrought iron or a glass beaker of different shapes, your chemical transformations might not continue as efficiently, but they will continue anyway. So it's not the architecture. Similarly, the flame that you apply doesn't matter very much. Neural networks can learn whether you use SGD or some much more advanced adaptive stochastic gradient technique. So you do need the right architecture, you do need the right optimizer, but these are not the thing that in the end makes or breaks what specific algorithms you end up with. So rather I'd say that's the data. Right? So for example, the data determines whether a single architecture learns many different tasks. I can train the same transformer architecture, basic transformer architecture, on modular arithmetic, and it'll learn modular arithmetic, or I can train it on natural language and I'll get a large language model. And similarly, many different architectures converge on the same internal representations. This is work going back to vision circuits, so some of the first interpretability work that was done. In particular, all of our current techniques for making models capable and also making them aligned look like shaping the data. So you feed it the entire internet, that's pre-training. Maybe you train it on some curated data sets, instruction fine-tuning. You might train it on helpful discussions from Wikipedia forums. Maybe you train it on preference data, highly distilled from humans in the form of a reward model trained on some other binary preferences. And increasingly, you're training also on model outputs, which is a very natural thing to do from the perspective of alchemy and chemistry, that you might want to distill compounds into in a succession of different chemical stages. And this is what alignment is in the present day. It's about changing the data distribution and then continuing training, doing more deep learning. Okay, so what's going on inside that cauldron? How are these different inputs combining to give rise to the final algorithm? Well, if we pull it apart, then what happens is that the data and the architecture together shape the loss landscape. That loss landscape, together with an optimizer, defines a learning trajectory, defines a trajectory through weight space. And that trajectory picks out the final algorithms we end up with, the final weights we end up with at the end of this process. So it goes from data to the geometry of the loss landscape to the learning process to the final algorithms. And really, the geometry of the loss landscape is the stage on which all of this interaction takes place, the interaction between architecture, data, and the optimizer. So that's how this works currently. You choose data that implicitly defines this loss landscape, which again steers the learning process towards outcomes that you hope are well aligned with what you wanted. Now, what's wrong with this approach is that we don't just care what the model learns at the end or how good its performance is. We actually care about how it accomplishes that performance. There's a difference between the model doing exactly what our intentions are, or doing 95% of our intentions, and then doing something catastrophically wrong in the remaining 5%. We care about how models accomplish the behavior because that's the important thing from the perspective of understanding how models are going to behave when you change the distribution, when you put them in a new environment. And that the problem with our current set of techniques is that we don't know how to constrain behavior in this tighter way. We don't know how to constrain what exactly the model does in order to accomplish this behavior. I'm going to identify two particular problems with this process. So first, the problem of generalization. This is the problem that two algorithms might appear to be the same. That is, they have the same loss on some data set or on some set of data sets, but nevertheless diverge dramatically in deployment if you feed it a new set of data drawn from a new distribution. So what we'd like to do is develop techniques. Let's say that this is the motivation behind it. Interpretability is developing techniques for disambiguating which of these cases you're in. Can you differentiate two neural networks that are going to behave differently under some distribution shift? I think you can't separate interpretability from this question of generalization. Now, on the other hand, we have this problem of learning. So what we'll see is that the learning process can sometimes get stuck, at least for a time, where the inductive biases of encoded into the geometry of the loss landscape can mean that our models don't perfectly learn our intended specifications. They might learn a simplification of our intentions. And that simplification might be dangerous. So what we'd like to do is to be able to develop the tools to write the algorithms more explicitly so that we can ultimately control generalization behavior as well. And so, again, this practical problem of alignment can't be separated from the scientific problem of understanding learning better. Okay, so in short, many problems in safety, problems of interpretability, of alignment, really boil down, at least in my perspective, to more fundamental problems in the science of deep learning and understanding these systems better. And it's possible that past a certain point, we might actually need progress on the scientific front in order to unblock further empirical progress. That brings us to SLT. So I'm going to take some time to go through the basics and introduce some of the basic definitions before we come back to how this interacts with these questions of generalization and alignment. Okay, so internal model selection. So what is learning? Well, we're going to take a Bayesian perspective where you start with some space of hypotheses That's H and squiggly H. And you have a prior distribution of beliefs over this space of hypotheses. Now, learning is the process of obtaining a posterior distribution over this space of beliefs. It's about updating your beliefs in response to some data set of n samples drawn from some true distribution, Q. And the way that we perform this mapping is through a model. And that model gives us a likelihood of the data set and of individual samples in that data set. Okay. So what you end up with in the Bayesian setting is that you perform this update rule through Bayes rule, as we see depicted here. Now, the first change we're going to make to this definition of learning is we're going to move to a parametrized definition of learning. So in practice, when we're trying to actually instantiate any kind of learning problem, we have to identify hypotheses with some kind of coordinate system, some way of finding the hypotheses and pointing to it and indexing into it. So that means that we're going to look at this from a parametrized setting, where now our hypotheses are weights. These are vectors in some d-dimensional space. The next thing we'll do is just rewrite it slightly. Okay, so I've just exponentiated the likelihood here into a negative log likelihood. This is an L sub n term. We'll see that this L sub n will play the role of a loss function in the kinds of learning setups we're familiar with from deep learning. Now, classically, there are really two kinds of learning hidden away inside of Bayes' rule. There's the problem of inference. This is finding the right weights. This is the problem that we've just described, where you're trying to find a probability distribution over weights given a data set for a fixed model class, for a fixed architecture. And then separately, there's the question of, do I even have the right architecture for the problem at hand? This is the problem of finding the right model for the data set. Because implicitly, there's this dependence hidden away here on the architecture, on the on the weight space that we've defined. Okay, so two kinds of learning. Now, what happens is you can often reduce the problem of model selection to a problem of minimizing a certain free energy. So what we've done is we can define a kind of Bayesian, a meta Bayesian update over different model classes, right? It's just Bayesian updates all the way down. And this meta process simplifies if you assume that you've seen lots and lots of data, because then most of the probability will concentrate on the model class that is best. And so you end up trying to find the model class WI that maximizes the probability of a given data set. We'll call this is equivalent to minimizing the negative log of that marginal likelihood, which we'll call f of n, the free energy. So what we're doing here is just the maximum likelihood approximation at a model class level. So we end up with this free energy minimization principle as the basis for model selection. What you end up with is asymptotically, the free energy has this form for so-called regular models. So it's equal to the best loss of your weights in this model class plus a constant term in the parameters times the log of the number of samples. As we'll see, for singular models like neural networks, this formula breaks down. So there's a more rich definition of free energy. The second term, we'll call it the complexity term, is no longer fixed to half the number of parameters, but it's now a variable term, which we'll call the local learning coefficient, that can be in general less than half the number of parameters. So just as we can recast the problem of model selection as a problem of minimizing a certain free energy, we can do the same really at the level of inference. So what we're going to do here is we're going to take a weight space on the left-hand side and partition it up into different phases, different regions of weight space, indicated by the capital W's. What you find is if you look at the free energy, of this model class, which is negative log of the denominator of Bayes' rule, that has this form. Go back here. It's negative log of the integral of the numerator. Now, you can just break this up into a sum over integrals over each of these regions. If you then look at the inside of this sum, you'll see that this is a formula that's very similar to the free energy we had above. So you can exponentiate this and you can end up with the overall free energy being given by the negative log of a sum over the exponentiated free energies of the individual regions. This is a very well-known approximation for the maximum function. And so what you end up with is, again, this kind of free energy minimization principle, but this time at the level within a model class. Okay. So what it tells us when we notice that the free energy has this now variable complexity term is that we're really not just trying to minimize the loss. In a Bayesian inference process over a singular model where different regions of weight space have different free energies, we're trying to find the region that has the optimal trade-off between the accuracy term, the loss term, and the complexity term given by lambda. This depends on the number of samples we've seen, so the trade-off can change depending on how much data we've sampled from our data set. And in this, we see a formalization of Occam's razor, right? The principal trade-off between performance and complexity. For regular models, this trade-off was boring because every region of parameter space has this constant complexity term. But for singular models, you can get more exotic things happening. You can get this internal model selection principle taking place, where the posterior doesn't immediately congregate around the optimal weights, but it moves around in a more interesting way. And so really we end up with these three different perspectives of Bayes' rule. Model selection, inference, and in between in this world of internal model selection, at least for singular models. Yeah, Billy.
Is there both maybe a theoretical and a empirical answer to where do you draw these boundaries between the regions? How are you chopping things up?
Yeah, Dan, do you want to take this one?
Yeah, that's a difficult question. So the appendices of the TMS paper has some theoretical discussion of that. I mean, empirically in that paper, it turns out to be suitable. I mean, in some sense, you can draw the boundaries. Under some conditions, you can draw them where you like because the effect of changing them, if the kind of posterior concentration is not very high nearby where you put the boundary, it doesn't matter asymptotically where you put it because it's like exponentially suppressed, that contribution anyway. But it isn't always clear that the relevant local minima are sufficiently well separated, both in like terms of the parameter space and also in terms of the gap between their losses and more generally free energies. And even if they were well separated theoretically, it's very unclear that you can like classify all the local minima and then know where to draw the boundaries. So I think in practice, this is like mostly a theoretical construction where, yeah, if you suppose that these kind of dominating critical points are sufficiently well separated in various senses, then this picture is valid. But in general, it could be much more complicated than this. So it could be that like you either have, you know, critical loci that are rather distributed and sort of interact in complicated ways, and the posterior can't really separate them very well, like with band structure and materials. So the like fully developed story of internal model selection could be quite complex in many directions. So we only just like have this very basic picture at the moment. Yeah.
But what I'm like hoping to do is like find a singularity, draw a little region around it that doesn't like cut through other singularity. Like I'm trying to surround it and not have any other complications in it.
That's
And
right.
but you're saying it might be difficult to do that in practice.
Yeah,
Can you say even theoretically, like, all right, if I know I have a singularity at this point, I can define this is the right distance away from it that I need to construct a region around. Like theoretically, that doesn't
Well, you can see the appendix of the paper for some like theoretical things that would be sufficient. I think it isn't like a very deep treatment. I mean, the thing is the relevant scale of distance. What scale do you mean, right? Like the scale is sort of dependent on n and also on the gap in the losses. There isn't like some absolute like the sort of natural scale in the parameter space given by the parameterization by real numbers, for instance, may not actually be the relevant one in which like the distance between critical points should be measured. So it's sort
okay.
of unclear. Yeah.
And does the partitioning matter exactly, or can I like can they just be separated connected components, these like regions?
It doesn't have to be a partition. Yeah. I mean, as long as the stuff that's left out of the partition is stuff that isn't competitive in terms of the posterior distribution at this given n, then like a sufficiently large n, those like leaving out those regions is not doing much harm.
Yeah, okay, thanks.
My question
Questions?
is, I'm wondering when this was first considered internal model selection. Is there a paper reference?
Not really, but it's in Watanabe. It's in the Grey Book, section 7.6. I mean, it's very terse and not spelled
Oh,
out
is it?
exactly in this way, but it's in Watanabe's book very clearly.
Oh, okay, the Grey Book
And
section.
he's, yeah, that's right.
Thanks.
And he spelled it out in more or less the way that Jesse was presenting it here, which it's been presented before in our talks. He gave a talk at some point spelling this out, elaborating section 7.6. So I learned about internal model selection, which I think is kind of a deep, interesting idea. I mean, Balasubramanian's paper on Occam's razor has this kind of story in the regular or near regular cases. But I think Watanabe is really the one who put forward this idea of internal model selection as a really important phenomenon, and then we kind of picked it up and ran.
Great, thanks.
Okay, I'm gonna continue. Zach, is it possible to go 15 minutes over?
Yeah, we can do that this time, and maybe we'll hold the questions, any more questions to the end for now.
Yeah, I'll try to go through it quickly. Okay, yeah, continuing. Okay, so this story of internal model selection so far is pretty abstract, so I want to give an example that's a little more concrete. So consider a case where we're learning a regular setting where we have just two hypotheses, a memorizing solution and a generalizing solution. Let's call them M and G. Well, again, the probability of either solution will depend on how much data we've seen. We'll update it using posterior solution. And what we can see is that learning which is the correct solution for a given data set is about minimizing the loss. It's about minimizing the difference in losses, or it's about finding the solution which has a lower loss. And so it's quite simple. We just want the solution that has the better fit. Now consider that we are parameterizing these two solutions, solutions in some continuous parameter space, which I've illustrated here as a 1D parameter space with a loss landscape that goes up and then down and then up again. So what's important here is that the probability associated to each solution is no longer just the probability at that point, but it's the probability of the region that contains the point. So Bayesian, if I'm allowed to use a word that people are familiar with, but that's not a word that I want to leave you with. So really the probability we're looking at here is integrated over these regions. So what you see here is that, well, that integral is naturally going to favor solutions that occupy more volume or that are broader in some sense. What you end up with in the singular setting is that learning is not just about trading off. It's not just about minimizing the loss, but it's about trading off loss against complexity. So the probability of the generalizing solution relative to the probability of the memorizing solution, I'm just writing it out here. This is going to be given by the differences in free energies of those regions rather than the differences in losses. Where the free energy is, as we saw earlier, defined as the negative log. The log should be outside of this integral. And it's because for singular models that the learning coefficient is not the same over the entire parameter space that we get a more interesting trade-off, where the model here will favor the generalizing solution over the memorizing solution, even for a time, even if the generalizing solution is worse. Now, this is still pretty abstract, but this is a phenomenon that you actually encounter in practice. So what we saw in this recent paper is that this trade-off between a generalization solution and a memorization solution actually can take place in real models trained with SGD. I'm not going to go into the details here, but the basic overview is that we trained a transformer to do in-context linear regression, where it sees XY, XY, XY pairs in context, and then it's trained to predict the Ys from the X's, where the Ys are generated according to a simple linear transformation plus some noise of the inputs for a fixed set of tasks. And as you vary the number of tasks, you see that the model learns different kinds of algorithms. It'll learn a memorization algorithm or a generalization algorithm. And using SLT and the kind of reasoning that I showed before, you can actually predict this trade-off between these two different kinds of solutions as you vary the task diversity, the number of different tasks, and as you vary the number of samples that the model has seen. This is building on earlier work by Reventos et al. And a larger literature looking at the in-context linear regression. Yeah. And so if you're interested in more, you should check out that paper. But the point there is that these kinds of trade-offs between different kinds of algorithms that have different complexities associated to them that lead to interesting dynamics really do take place in models. And moreover, it might actually be relevant for safety. So you can imagine that you might actually prefer a model that has very carefully memorized the specification you give it to a model that has, done a sloppy job of internalizing some vague heuristics and pretending to be behaving in line with your specification, but really overgeneralizing and doing the wrong thing. So this kind of trade-off is relevant for understanding what algorithms models actually end up with. Okay, that brings us to generalization. Okay, and I want to start with a motivating hypothesis that informs why we think SLT is relevant for interpretability. The idea is that something we call structural Bayesianism is the idea that somehow the model internals, the algorithms the model has learned, are reflected in the local geometry of the loss landscape. If that's true, and if you can probe this geometry to a sufficient degree of resolution, and if it's possible to invert this relation, at least to some degree, that gives you a basis for interpretability. Maybe instead of trying to interpret the algorithm directly, we can get at it by interpreting the geometry, by measuring the geometry, and then inverting this mapping to extract the algorithms that a model has learned. This is the basis for using the study of geometry informed by SLT to try to get at a suite of techniques for interpretability. So I'm going to give an example in terms of the local learning coefficient for highlighting how this comes up. So as we saw in the free energy formula, this second term is this complexity term. It's what we call the local learning coefficient. So yeah, what else is it? What is it really? Well, it's got these two sides to it. So on the one side, you can see it as a measure of geometry. And on the other side, you can see it as a measure of algorithmic complexity. So on the geometric side, the learning coefficient is the volume scaling rate. So if you consider some loss landscape, and you look at a local minimum, you can ask how many solutions are almost as good as the solution. What's the volume? In this case, what's the area of the gray region, or the surface area of this water in the loss landscape, and how does that vary with my tolerance epsilon? What you'll find is that the volume will generally scale like some constant times epsilon to the power lambda as you get closer and closer to the bottom of this landscape. To look at a few examples, if you have a parabola, then the learning coefficient will be maximal. And in this case, you've got 2 dimensions, so 2 divided by 2 is equal to 1. If you have something more interesting like x to the fourth plus y to the fourth, then the learning coefficient can be less than this. In this case, you'll get a learning coefficient of a half. For something even more interesting, x to the fourth times y squared, you'll get 1/4. So what you're seeing here is that the learning coefficient measures how quickly the volume scales near the bottom. And it's doing this in a way that's sensitive to geometric information that goes beyond second order. Right? At the minimum for these second 2 examples, the Hessian at the origin is the zeros matrix. So second order information can't distinguish these 2 examples. But the learning coefficient actually tells us that the second example is more degenerate. There are more ways you can vary the parameters without actually changing the loss than in the middle example. So the learning coefficient is this measure of geometric degeneracy. How many ways can I perturb weights without changing the loss? It's also got this information theoretic interpretation in terms of being the number of bits required to specify where you are up to an additional doubling of precision. So if you wanted to have the error, how many bits do you need in order to specify your location? No, the real definition is the algebraic geometer's definition. So this is how the learning coefficient shows up inside of SLT as the real log canonical threshold, or RLCT. I'll save you the details here, but if you're interested, go read Watanabe's riveting book. So what we see here is that the learning coefficient has these geometric interpretations. It tells us something about the loss landscape locally. On the other hand, I told you that it has something to do with model complexity. You can see this by considering minimally singular models. Suppose you have a model where it doesn't use one of its parameters. It never uses it. You can set it to an arbitrary value without ever affecting the model's output. In that case, there will be a degeneracy in the loss landscape in that direction parameter space. And so the fact that you have this simpler model that doesn't use all of its parameters is reflected directly in geometry. That's the sense in which the LLC is like an effective dimensionality. In general, the LLC is more than just an effective dimensionality because you can get these partial contributions. So the learning coefficient isn't just a half integer multiple. It can be any rational number. You can get partial contributions from different weights. Going beyond this, we have reason to think that the learning coefficient measures additional kinds of algorithmic structure. So in programs of singularities, work by Dan and Will, you can see that in the setting of noisy Turing machines, the learning coefficient seems to capture something like error correction. So is your model able to produce the same outputs even if there's a mistake in the internal computation? Maybe related to other kinds of high-level algorithmic structure like modularity, right? How's your network split up its computation internally, as well as things potentially like speed priors or other things like this. So what we're seeing is that in the geometry, we get this high-level information about the kind of algorithm we end up with. The LLC is also linked to generalization directly in the theory. So in SLT, the main kind of generalization error we care about is the Bayes generalization error. This is the KL divergence between the true distribution that generated the data that we're looking at and your posterior predictive distribution, which is the prediction that you would get if you use the entire posterior distribution to make your predictions. You run your new sample through each weight and then average those predictions according to how much probability that weight gets under the posterior. So classically, because the learning coefficient is this d over 2 term, the Bayesian generalization error is very, very large in general. But because for singular models, the LLC can be less than this, you can end up with much better generalization than you would naively predict from the parameter count. And this is essentially the resolution to the classical mystery of why large over-parameterized models are able to still generalize very well. So the learning coefficient has all these different interpretations. It's got these geometric sides to it. It's got these complexity sides to it. Usually you can't actually access this directly. So what we're seeing here is some theoretical reason to think that our ambition to read algorithms off of geometry might be possible, at least in theory. But how do you actually turn this into practice, into some engineering interventions? Well, the idea is going to be that you can try to sample points in the neighborhood of your choice of weights. That's the methodology. We're going to draw samples from the local posterior and then compute statistics over these samples and use that to try to reconstruct the algorithm or high-level features of the algorithms we end up with. And then perhaps, we can invest more compute to get more samples to come up with even more accurate estimates of what kind of algorithmic structure the model has ended up with. So in this work by Dan's here, Zach's here, and others, what we can see is it's possible to actually, in some cases, scalably estimate the learning coefficient up to hundreds of millions of parameters and do so accurately, at least in systems where we have some kind of ground truth. So using stochastic gradient MCMC techniques, you can estimate this theoretical quantity. This requires two ideas. So on the one hand, we introduce this formula. This is an estimator for the LLC. And what it's telling us is that we can estimate the LLC by looking at the average increase. That's what this expectation value is. Average increase in loss from our starting checkpoint or starting local minimum to points in its neighborhood. So we'll use SGLD, stochastic gradient Langevin dynamics, to estimate this expectation value, which is essentially just alternating SGD steps and Gaussian noise. And we'll use localization. We'll add a confining prior at our local minimum to make sure that our chains don't veer off too far. With these two interventions, it seems to be possible to actually scalably estimate the LLC. Okay, so we have on the theoretical side some reasons to think that these geometric measurements tell us something about algorithmic structure. Empirically, we have a tool for at least measuring the learning coefficient from the geometry. So how much more information can we actually extract from the loss landscape? That's maybe the key question motivating continued research into SLT for interpretability. What new tools can we develop? What new measurements can we develop? How much information is actually reflected in the geometry? It brings us to the final problem I'd like to talk about, which is learning. So how does training data actually give rise to the algorithms that models end up with? So we looked at structural Bayesianism as this hypothesis that motivates an interpretability agenda informed by SLT. On the learning side, we have to start with the observation that ultimately what sits in between ultimately what determines the algorithms that we end up with is the data. And it's the geometry that sits in between the data distribution and model algorithms. So here, the idea is going to be that if the mapping from data to geometry through the learning process to the algorithms that we end up with is sufficiently faithful that we can invert it, at least in part, then potentially that gives us ways to convert constraints on our algorithms into actual interventions in training data. Maybe we can come up with ways to better structure the curriculum that the model is trained on, or better choose the data that we use to make models helpful, harmless, and honest. Okay, so let me explain the S4 correspondence in a little more detail. So this is S4 for 4 kinds of structure. What we see is that it's statistical structure in the training data that determines the geometric structure in the loss landscape. That in turn, together with the optimizer, steers the learning process around and picks out the final algorithms we end up with. And this is what we'll call the S4 correspondence. We expect this to be true in general for many different kinds of learning process, right? Whether you have a Bayesian learning process or SGD, It's the case in general for dynamical systems theory and across many areas of math that it's the geometry, and in particular certain key features of geometry, where the singularities are and how they're structured, that guides this learning process. So the idea for us is going to be that we'll use the theory to study the question of how the posterior changes with the number of samples, and then link this to the kinds of distributions of final weights we end up with once we train models through practical techniques like SGD. And then the real hope here is that we can invert some of these arrows to go backwards from algorithms to changes in data. To give you an example of what this pipeline looks like in practice, I want to show you how the learning coefficient can be thought of in terms of these different levels. So, consider training a model on different kinds of data distributions, some of which are simpler than others. So for example, if you have a deep linear network, you're trying to learn some linear transformation. Y is given by t times x. And suppose that your model involves these multiple matrix multiplications. Well, if that's the case, then if the T matrix that you're trying to learn is not full rank, what that means is that your model will be more degenerate. It'll have an implementation associated to that. It has more free parameters. So I can set the A matrix here to 1, 0, 0, 0. And if that's the case, then these two entries right here don't matter because they get canceled out by the zeros in the first matrix. So what we see is that the simpler model, the simpler implementation that's lower rank, has more degeneracy. You can see this more generally. So if you have a dead neuron in a ReLU MLP, that leads to free parameters in the output weights. Similarly, if the ReLU is always activating, so it's never dead, it's never inactive, then really it's not a nonlinear unit at all, and you regain the kinds of degeneracies that you see in the deep linear network case. So here too, if your model is using fewer of its elements, it's not using all of its activation functions fully, and that's going to lead to a simpler implementation that's more degenerate. So there's a link between data and degeneracy. At the same time, what we've seen is that the posterior, through the free energy formula, prefers these more degenerate solutions. So solutions that are simpler occupy more volume in the loss landscape, as quantified by the learning coefficient. This means they're actually preferred by the learning process in a way that you can make precise by looking at the free energy. And come back to this. And these solutions generalize better. They're simpler, so through an Occam's kind of razor argument, they actually perform better. And again, we've seen this made precise through the Bayes generalization error. This is a very high-level description, but it can be made precise using SLT in the in-distribution setting. Okay, that's still quite high level and a little rough. So can we do better than that? We'll come back to that in a second. So we looked at this question of, this should say, so we looked at this question of interpretability as motivated by the hypothesis of structural Bayesianism. Now, what SLT does is, let me cut back a little bit. Sorry, Zach, I'm going to give you an editing job right here. Okay, so I want to go here. Referred by the posterior. Okay. And what this internal model selection principle that we saw earlier gives us is it predicts that the learning process, as we sample more and more data, will consist of a series of phase transitions, right? Where if you look at two different regions, where one region has higher loss than the other region, but the complexity is lower, then the Bayesian posterior will initially favor the simpler, higher loss region, W1, before eventually the free energy is minimized by the second region. So at the point at which the free energies of these two regions are equal, you get this phase transition. And then the posterior will jump to the next region. Now, what we've seen is in practice that these phase transitions are real. So you can see them in deep linear networks. You can see them in toy models of superposition very clearly, where the model has one kind of solution. It learns a new kind of solution that's linked to this formation of a leg and then retracting a leg. It undergoes a final phase transition in which it learns one more leg, and each of these discrete changes is a phase transition in the SLT sense. So simpler patterns are more degenerate. You can perturb their implementation in more ways without actually affecting them. That means they occupy more volume. Because they occupy more volume, they're easier to find by the learning process. Because they're simpler, they generalize better. And all this can be made precise by the language of SLT. So this observation of phase transitions, or the prediction of phase transitions, motivates the original series of applications we came up with for SLT in AI safety, which we call developmental interpretability. This is the idea that maybe it's easier to interpret the series of phase transitions over training than it is to interpret the final model you end up with. And through a series of papers, we've shown that, first of all, these kinds of phase transitions do appear to be real in realistic architectures, transformers trained on real data sets, even if these architectures are still quite small. Using this developmental interpretability perspective, you can actually learn new things about models and what's going on inside of them, things that you would have had a hard time discovering if you just looked at the final weights. We've looked at using SLT for a kind of automated circuit discovery set of techniques in this recent paper on susceptibilities and structural inference. You could potentially use it for even more. Okay, so this link between the LLC and this pipeline, this S4 correspondence, is still pretty high level. Can we be more precise about it with this new data that we've gathered from these language models, from these real world cases? Well, in this first paper that I mentioned, what we found is that in these simple two-layered attentional language transformers, the loss behaves very smoothly, it goes down in a very steady way that's kind of boring. However, if you look at the learning coefficient, it goes up in this stepwise pattern. And you find that the critical points in this curve actually correspond to points at which the model has learned some new behavior. So the model initially learns bigrams, then it learns n-grams and skip n-grams. It learns the induction circuit in two parts before finally converging. And so you can actually find phase transitions in real models using the learning coefficient. So what we're seeing here is a link between different kinds of patterns in data and the series in which the model learns these different kinds of patterns. So it's learning them sort of from simple to more complex. And in a way that's revealed that you can actually detect in an unsupervised way just by looking at this measure of geometric degeneracy. In follow-up work, we looked at these refined learning coefficients where you can measure this complexity measure for a subset of weights, or a component of the model, like an attention head, or for a different data distribution than the one you trained on. If you look at this, you study this over training time, you see that you can use these weight-refined learning coefficients to track how different attention heads differentiate into different functional roles. So on the bottom here, we have induction heads. On the top, we have heads that memorize increasing numbers of different n-grams and multigrams. So moreover, the learning coefficient actually seems to track the different numbers of things that different heads memorize. So we're starting to see, I'll jump through the rest of this, is a link not just between the data and the learning process, but also which specific heads learn which specific patterns of data and the circuits and how they compose together. So we're starting to see a more complete picture for these simple two-layer transformers of this S4 correspondence. More recently, this work on spectroscopy and susceptibilities and structural inference tries to, in some sense, bypass the learning process, and it looks directly at the link between data and components of the model through geometry. Jump through this. So we're seeing more and more ways in which this S4 correspondence is being completed for these simple models. Okay. So this is still really interpreting models, developing additional tools for interpreting models through their learning process. Can we at some point turn this around and actually say something about how to steer the learning process through the choice of training data to make models more aligned? The answer is currently we don't know, right? But we think this might be possible. We think it might be possible to develop better alignment techniques, better ways of choosing training data to make models more robust. What that could look like is fleshing out this S4 correspondence in a more complete ways. So statisticians have many different kinds of ways of talking about statistical structure, correlation functions, efficient statistics, all kinds of things. Algebraic geometers have many more ways of talking about geometric structure than just measurements of degeneracy. They're much more complicated ways and richer ways to talk about what's going on in the loss landscape. Similarly, if you talk to dynamical systems theorists or developmental biologists, there's this whole literature on different ways of talking about structure inside a dynamical system. Finally, talk to a computer scientist or a biologist about different ways of talking about algorithmic structure. The hope is that with further research, we'll develop a more and more nuanced understanding of the links between structure and these different levels. And fleshing this out is the hope for the S4 correspondence. Depending on how thorough those links are, it might be possible to, in some sense, invert this relationship. And that would be a set of techniques for choosing training data. So with that in mind, maybe the future of training models looks less like alchemy, right? It looks less like throw all of your reagents together in a big cauldron, start stirring and hope for the best, and more like industrial chemical engineering, where you actually know which reagents to combine, in which order, at what concentrations and pressure, in order to elicit the kinds of compounds you want out the other side. We're starting to see the shapes of what this might look like, where we can use all of our inputs to bring to bear on the problem of deciding what kinds of algorithms we end up with at the end of these learning processes. That's it. So to recap, we talked about AI safety and the possibility that many problems in AI safety are really problems of understanding on a scientific level what is going on inside of deep neural networks, how their learning processes work, and how and why they generalize. We talked about SLT and how it predicts that for neural networks, models should undergo internal model selection, where you see this changing trade-off between complexity and performance over the course of the training process. We looked at a few examples, this toy example of memorization versus generalization, and the more realistic example of retreat from ridge. And then we looked at these problems of generalization learning in a bit more detail. We looked at this motivating hypothesis of structural Bayesianism and the S4 correspondence, telling us why looking at geometry is very natural for trying to come up with new tools for interpretability and potentially new techniques for alignment. And then we looked at various examples from recent literature showing these links play out. With that, we can wrap up, and if there are any questions, I'm happy to take them.